lesson is a power supply. The transmission lines are power for the correction. So power supply is important for the transmission line. When the power supply is poor, the devil is a line current will be higher. Line current higher, and the devil is a lot of power loss. A lot of power loss means the line efficiency will be poor. Line efficiency can be poor, or the line voltage draw will be higher, and the voltage regulation will be poor. So those are the disadvantages of the lower power factor. And because of this one, in the power transmission system, we need to improve the power factor. So there are two ways to improve the power factor. One thing is you can for a very large power station, we use free running synchronous motor. Synchronous motor power factor adjusted depending on the excitation. So over excited synchronous motor, they got the leading power factor, and excited with the lagging power factor. So the power factor can be adjusted by the synchronous motor. So those synchronous motors are running in the parallel with the bus bar, and they provide adjusted the power factor. So in the meantime, for the smaller power station, we use a static bar control system. So FDC system, static bar control. Static bar control system means we utilize automatic switching device. Our automatic switching to the for the capacitor. The capacitors are automatically switched. So that if you want more leading power factor, we switch on the capacitor. If you want a more lagging power factor, we switch on the inverter. So by the way, we adjust the power factor. So that in the tonight's lessons, we will study how to calculate the appropriate size of the capacitor to maintain the standard required power factor. So that in the power factor correction, we use a poor power factor. Poor power factor can create this higher line current. Higher line current. The more voltage drop, and the more power loss. So those are the disadvantages of the for poor power factor. Therefore, we need to improve the power factor. It needs to improve power factor by, so this is a free running synchronous motor. Free running synchronous motor. For substation. And SVC. So SVC is a static bar control. So this is an automated variables power factor control. Automatic variable power factor control system. So SVC is a static bar control or the automated variable power factor control system. Need to use apply it for the power factor. So this is the way to improve the power factor. And therefore, before we detailed study the power factor characteristics, so this is the power cycle. So power cycle is a horizontal line represents the active power. Active power. So this is P. And unit will be the watt. And vertical line represents the apparent power. So this line represents this angle is a P power factor angle. This is apparent power. So this is a V multiplied I. So this is a VO N. So this multiplied represents the reactive power. So this is a VI. So this is the active power is a VI cos theta. So this is a VI sin theta. So the unit will be the bar. Active appearance and the reactive power we can calculate. This is for the single phase system. For the three phase system, so active power is a VI, usually VI cos theta. The unit will be watt. And so reactive power. So this is usually VI sin theta. So that will be the bar. And apparent power. this becomes a root 3 VR. So this is becomes the both ends. So those are the active, reactive, and apparent power relationship. So we can also write down the equation for the complex power. So complex power equation. So S is both ends. Complex power S is equal to P plus or minus JG. So this is the equation. So S is a complex power. S is a apparent power. P is a active power. And Q is a reactive power. So plus 4 is leading power factor, and minus 4 is lagging power factor. So this is where we can calculate the power factor. So in this case, in the power calculation, so we try to determine set up the appropriate power factor for the special line, and then we also need to select the appropriate side of the capacitor. So by this way, you can optimize the power factor on the line, and then you can also set the appropriate line current. So now we saw the one program. So in this case, you also need to add up all the power factor, or active, reactive, apparent power on the load, and then you have to calculate the appropriate side of the capacitor. So this product three-phase 460 volt, 3 half loads are connected together in the industrial installation. So we have to calculate the total load, to the power factor, the value of the capacitor required to raise the power factor to 0.95. So in this case, load 1 is 100 kVA, power factor 0.75 lagging, and load 2 is the 50 kilowatt, power factor 0.8 lagging, load 3 is 20 kVA, so 90 degree leading, and also load 4 is 60 kilowatt, 90 kVA, and the lagging. So those are the 4 loads. So those 4 loads are we can connect it. So load 4 is 90 kVA lagging. 90 kVA lagging. They are 4 loads. 4 loads there. Load 1 is 100 kVA, 2.75 lagging. Load 2 is 50 kilowatt, 2.8 lagging. Load 3 is 20 kVA, 90 degree leading. And load 4 will be 90 kVA lagging. So they are 4 loads. So firstly we calculate for the load 1. Load 1 means in this case power factor is given as 0.75 lagging. So you firstly find the angle theta. Cos theta is 0.75. The theta is equal to cos inverse 0.75. So that will be 41.4 degrees. So this is the theta. So then you can find this power angle. So this will be the P1 means the 100 cos theta 1. P1 is equal to 100 cos theta 1. So 100 multiplied 0.75. So this one will be 75 kilowatt. So P1 is 100 cos theta 1. So 100 multiplied 0.75. So you got 75 kilowatt. So this is the power 1. And also you also need to calculate for the Q1. Q1 means sin theta 1. Q1 means this is for the calculate. So 100 sin theta 1. 100 sin theta 1. So this is 100. 100 is a kVA. Because the point is that this one here, this line is 100. So this is angle theta. So 100 this angle theta is 41.4. So 100. So this side is 100 is a hydro value. So horizontal line is the real power. This is adjacent side. And Q1 vertical line means that this is the opposite side. Opposite side, so that you have to utilize as a side. So Q1 is 100 sin theta. P1 is 100 cos theta. So 100 cos theta means 100 multiplied by 0.75, you got 75 kilowatt. Q1 is 100 sin theta. So 100 multiplied, sines are 41.4. So 100 sin 41.4, so you got 66.1 kVAR. So we got the two components. T1 and T1 we can calculate. This is for the load 1. And load 2 is a 50 kilowatt. And this one is a popular lagging. So secondly you can calculate for the load 2. So load 2 means the popular engage given. So this one is popular lagging. So you explain it out. Cos T9 is 0.8. So T9 is equal to cos n by 0.8. So you got it 36.8 degrees. Then you can find the thing. So this one is the angle here. So this angle is 36.8 degrees. And then this is a 50 kilowatt. So this one is a 50 kilowatt. So this component is 50. Tangent at 36.8. Because according to tangent, the opposite side is equal to the horizontal and the tangent theta. So then we did 50 multiplied tangent 36.8. So you got this 37.5 kVAR. 37.5 kVAR. So this is for the vertical line. So this becomes Q2. Q2 is 37.5 kVAR. P2 is 50 kilowatt. So this is for the load 2. And then also you can calculate for the load 3. The load 3 is a 20 kVAR. That is leading. So this means that leading power means only the capacitor. So this is a 20 kVAR. 90 degree leading. So this one will get this component. Q3 is equal to 20 kVAR. And the low 4. The low 4 is a 90 kVAR and a lagging. So this is the low 4 is lagging means 90 kVAR and lagging. So then we use this component, this one. This one, lagging means that this is a Q4. So 90 kVAR. So those are the four loads. So now that these four loads are made a connection all together. So we have to combine the all load 4. So load 1, load 2, load 3, load 4. We need to add the real power and the reactive power. So that you can add the total power. So now you can add the total power. How you draw? Firstly, you have to draw the power target. Power target means that load 1 is this one. This is a horizontal line and a vertical line. So then we use the 41/4. 41/4. So this is the P1. P1 we use the 75. Q1 we use the 66.1. And this is for the P1 Q1. Load 2 is also 50 here. P2 we use the 50 kilowatt. And this one is the Q2. Q2 will be the 37.5 kVAR. Okay, so this is the load 2. Load 3 means so this is the all of downward because the lagging power down. Lagging power down, everything will be going downward. But the load 3 is leading 20 kVAR leading, so this is a 20 kVAR positive. So this is a Q3. 20 kVAR leading. And finally the Q4. Q4 is a downward gate. So 90 kVAR are lagging. 90 kVAR lagging from here. This is a 90 kVAR. So this is what a Q4. Okay, this one lagging. So finally you draw a diagram. So this is a starting point. This is final ending point. So you join this one. So that will be the total. So this means that total power setup P2 right here, this component. And this is total reactive power P2 right this component. So total power, real power, active power is a PT, total reactive power is a QT. So this means that firstly you draw it as lagging. P1, Q1 lagging to go down, P2, Q2 lagging go down, Q3 is a leading so up, and Q4 is a lagging to go down. So this is final ending point, this is starting point. So you join these 2 points. So this blue line indicates the total So there's a power cycle. So then you can add the all PD or duty together. So that we add the all PD. So then we P1 plus P2 plus P3 plus P4. So P1 is a 75, P2 is a 50, P3 0 and then P4 0. So you can calculate that total PD. So total PD you calculate it. This is 125 kilowatt. And also the QT. QT is that you have to add. Q1, Q2 is going down. And Q1, Q2, Q4 going down minus Q3. So that will be Q1 plus Q2 minus Q3 plus Q4. So then you add Q1 is at 66.1 plus Q2 is at 37.5, Q2 is 20 and this is 90. So by solving this one, you got this Q2 there. So Q2 there will be that 173.6. So 173.6 kVAR. So this is a P2 there and the Q2 there we got. And then you can also calculate the total apparent power S2 there. The formula is square root of P2 there square plus Q2 there square. Then you got the S2 there. So PD square is 125 square. And QD square is 173.6 square. So by solving this one, you got the S2 there. So S2 there will be the 213.9 kV. And then you can find the tangent theta. So this is a D. D will be the tangent theta. So tangent theta is you can calculate. So the loop you can calculate. This is for the A. This is for the total load. And to the power factor. To the power factor, you have to calculate tangent theta. So tangent theta T. So the formula will be that Q total by P total. QT by PT. So Q total we can calculate is 173.6. Then 125. So by solving this one, you got a tangent theta will be there. So after that you can find it out. So the tangent theta you can calculate, and then you can also find it out theta T. So this is tangent inverse 173.6 divided by 125. So by solving this one, you got the 54.07 degrees. So this is the theta T. And then you can calculate for the power factor to there. So cos theta T. So the cos 54.07. So this one, we calculate the cos, so that will get 0.586 lagging. So cos power factor to there is equal to 0.586 lagging we got. Okay, so this is for we can calculate for the power factor. So this is for we can calculate for the off power factor by this way. So the cos angle theta is 0.586 lagging. And second step. So value of capacitor required to raise the power factor to 0.95. So in this case, we have to utilize the power factor. So this is the total power factor is what you got is 0.586, and total power factor angle is 54.07. So this is the overall load power factor. But this one is the power factor is poor. Because the power factor poor and the power factor 0.586 is poor. For the industrial load power factor should be the 9, around 0.9 or more than the 0.9. That will be the best. And because of this one, we need to raise the power factor. Only thing you can use is you can connect the capacitor across the terminal. Then you can improve the power factor. So this means how to make the power factor is we have to use the connection. Connection means that this is the power factor capacitor. So this is 3 line here. 3 line means that those are the industrial load. This is the motor load, or this is lighting load, like this. So you make a connection. So this one also we can connect. Okay, so this is one is this is industrial load. So this is the formula we are getting. So to input the formula, you need to connect the capacitor bank. So capacitor bank can be the either star or delta. So this is a star connected capacitor bank. So we connect the capacitor bank like this way. Or you can also connect the capacitor bank in delta. So this is the capacitor bank in delta. So star or delta. So this is star capacitor bank. Or this is delta capacitor bank. Star capacitor bank or delta capacitor bank need to be connected to the input the power factor. So now that this is the way to connect, so you need to calculate the value of the capacitor. So that before you make the value of the capacitor, you also need to find out how much kVAR need to be improved. So this is the you have to calculate. So therefore you have to redraw the power factor. Original power factor is power to there. Power to there all is given. The PD is 125. And QD is only given also here. QD will be 173.6. So this is the theta 1. Theta 1 is only given that theta 1 will be 54.07. So this is for the original power factor. And then you also need to calculate for the final angle. So final angle is this is the Q2. Theta 2. So theta 2 is we have to enter the power factor 2, 0.95 lagging, so that you can calculate that theta 2. Theta 2 is equal to cos inverse 0.95. So you got the 18 degrees. So this is the theta 2 is 18 degrees. Okay, so this is the Q2 data. This one and it can need to be calculated. This is for the input. Original QD is this one. Original QD this is this one. So how to calculate? So this is our QT2 here. This is for the Q2. So you have to calculate that this is the delta Q. Delta Q you can calculate. The formula will be the QT minus PT tangent theta 2. So then you can calculate the QT. Q2 there is a 173.6 minus PT. PT is a 125 and the tangent theta 2. So this is a 18. So by this way you can calculate the Q delta Q. So this delta Q we can calculate from here. Then will be the this delta Q will be the 131.25. So this is the 131.25 kVAR. So this is for the capacitor. So this kVAR need to be cancelled. So they are cancelled by capacitor bank. And because of this one, you can also calculate the capacitor bank. So we now utilize for the capacitor per phase. Capacitor per phase. Capacitor per phase. Can we calculate that? PDA is equal to the Q delta Q divided by 3 phase voltage square multiplied with 2 pi into S. So delta Q will be 131.25 into 10 power 3 divided by 3 phase voltage. So 3 phase voltage you can calculate 3 multiply phase voltage. So in this case, you can either connect the capacitor bank by star connection. If you connect it for the star connection, phase voltage is line voltage divided by √3. So this is 415 divided by √3 square. Multiply 2 into 3.1416 multiply 50. So by solving this one, you got the thing is 0.7 into 10 power minus 6 farad or 2417.7 microfarad. So we can calculate like this. So this is what is power improvement. So we can initial plant conditions initial plant is higher lagging power. So by this way we can improve the power by this way. So we connect either star or pair connection branch and then we can improve the power. In the above program, if the capacitor selected in data, what will be the value? So we can also calculate the same formula. CBA is equal to, so this is a theta Q divided by 3 CBA squared multiplied 2 by F. 3 CBA squared multiplied 2 by F. So the delta Q we already calculate. So we already calculate the delta Q. Delta Q is 131.25 into 10 power 3. 131.25 into 10 power 3. Divide 3 multiply 6 voltage. 6 voltage means all the delta connection. Delta connection means line voltage and phase voltage are the same. So you can substitute the 415 volt. So this is a 415 square. So 2 multiply 5 is 3.1416 and frequency is 50. So by this way you can calculate the capacitance value. So the capacitor value will be about 3 times smaller. So by this way you can calculate for this capacitance value. Okay, so the second problem, along with a power factor on the 0.6 lagging, the CP is 2000 watts. And from the 240 volts are 50 hertz supply. So is required to correct the power factor to 0.9 lagging. So when we find the original and the final current value. So this means the load is a 2000 watts. So this is the original Y is a 2000 watts. So this is P. Okay, so then so correct the power factor. So power factor 0.6 lagging. So this is the cos theta 1 is 0.6. Therefore you can calculate theta 1. So cos inverse 0.6. So that will be the 53.2 degrees. So cos theta 1 is 53.2 degrees. And then this is for the original power factor. And final power factor is 0.9. So this is the cos theta 2. Cos theta 2 is 0.9. Then you can calculate theta 2. So cos inverse 0.9. So then we use 26 degrees. So original power factor is 0.6. So angle is 53.2. The final power factor is 0.9 and is at 26 degrees. So this is a load. So in this case, our student power is 2000 watts. The original power factor angle is at 53.2. So that way is at 53.2. Theta 1 is at 53.2 degrees. And final power factor angle will be at 26 degrees. So that way is the final power factor angle here. This is at 26 degrees. So this is for you get to calculate the big capacitor value. So 2000, there's a horizontal line, and theta 1 is 52, theta 2 is at 26. So it is required for the power factor. So we have to find the original and the final current. So original and final current means the power. So this is for this is it doesn't phase. So this is a single phase system. Because the single phase system means that you see a 240 volts. 240 volts is a single phase supply. Therefore, you can calculate P1 is equal to V1 I1 into cos theta 1. So the original P1 is we can calculate for 2000. So voltage V1 is a 240 volts. I1 and the cos theta 1. So cos theta 1 is that we already calculate. So this one will be 0.9 0.6 power factor. So this is a multiplied 0.6. Then you can calculate for the I1. I1 will be 2000 divided by 240 multiplied 0.6. Then you got the I1 will be 13.9 ampere. So this is and also you can calculate for the P2. P2 is equal to V2 I2 cos theta 2. So the final power is also the same because only we input is a power factor. So the power is the same. So you put the 2000, P2 is 240, I2 don't know, cos theta 2 you already know that this is a 0.9. Then you call it I2. So 2000 divided by 240 into 0.9. So then you call the current I2. Current I2 which is a 9.26 ampere. So I1 and I2 we can calculate by this. So this is for the A. As D, the value of the components to be added in parallel with the original to require to achieve the required power factor correction. So in this case, this component is power factorizing into, so these are delta bar. This component is a delta 2. Delta 2 need to be the cancel. Because of this one, you have to calculate the capacitance value. So we use the formula. This is for the single phase system, so we don't use the three-phase system. Capacitor phase equal to delta 2 divided by 3 phase voltage square into 2 by x. This is for the three-phase of power factor. So then maybe star or delta. Star or delta, you just substitute the voltage value. Star value is a 415 divided by V3. Delta is just substitute the 415. But for the single phase, there is a no 3. So capacitance value per phase you can calculate. Capacitance value per phase is equal to 2 delta 2 divided by VV8 square multiplied 2 by x. So then you substitute here. So delta 2 value you can calculate. Delta 2 you need to calculate. Delta 2. Delta 2 you can calculate P into tangent theta 1 minus tangent theta 2. Okay, so this is that we can calculate for the delta 2. So this is what is the angle theta you need to calculate. So P is at 2,000. Tangent theta 1. So that will be the tangent 53.2 minus tangent theta 2. So tangent 26. So by solving this one, you can calculate the delta 2. So delta 2 will be 16.1698 bar. This is so then you can calculate the capacitor per phase. T per phase delta 2 is 1698. Phase voltage square is at 240 square. 2 pi is at 3.1416 and frequency is 50. So by solving this capacitor value will be 5.41 into 10 power minus 6 farad. Or this is a 5.41 microfarad. So this is by this way that you can calculate for the power factor improvement. So since we use a similar formula, capacitor phase is equal to delta 2 by 3 phase voltage square into 2 by. This is for the three-phase system. But for the single phase, there is a no 3. Capacitor phase is equal to delta 2 divided by phase voltage square into 2 by x. This is for the single phase. So that those are programs are original power factor need to be the input to new power factor. So we are calculating the required capacitor value for the capacitor power factor improvement. So that in the transmission line system, we need to input the power factor. So the poor power factor can result in higher line current, and then higher power loss, and also to compensate the higher power loss, you have to utilize the bigger wire size so that it will be economic there. And similarly, you need a stronger tower, voltage regulation will be poor, so those are disadvantages. And this is why we need to input the power factor. So how